We all learn about gravity early on. From a young age, we are introduced to the concept in our classrooms. We see it in our textbooks, and our teachers explain it to us with simple experiments and demonstrations. We know it makes things fall down. Whether it's an apple dropping from a tree or a ball slipping from our hands, gravity is the invisible hand that pulls everything towards the ground. It's why we stick to the ground. It's the reason we don't float away into the sky, and why we can walk, run, and jump with confidence that we'll always come back down. But what if I told you gravity isn't a force at all? This might sound like a radical idea, something that challenges everything we've been taught. This might sound strange, even impossible. How can something so fundamental to our understanding of the world be anything other than a force? But the universe is full of surprises. It's vast, mysterious, and often defies our expectations. To truly understand gravity, we need to open our minds to new possibilities. To truly grasp gravity, we need to challenge our assumptions and embrace a new perspective. We need to look beyond the surface and delve into the deeper workings of the cosmos. For centuries, we believed that gravity was an invisible force pulling objects towards each other. This idea, first proposed by Isaac Newton, revolutionized our understanding of the natural world. This force, we thought, was responsible for holding us to the Earth. It explained why we stay grounded and why objects fall when dropped. It explained the moon's orbit around our planet. Newton's laws of motion and universal gravitation provided a framework that made sense of the celestial dance we observe in the night sky. It even seemed to govern the movement of stars and galaxies across the cosmos. The same principles that kept our feet on the ground also seem to apply to the vast, distant reaches of space. However, this understanding, while intuitive, is incomplete. It's like having a piece of a puzzle and thinking you have the whole picture. There's more to the story than meets the eye. It's like looking at a puzzle piece and thinking it's the whole picture. To see the bigger picture, we need to consider the other pieces and how they fit together. To see the bigger picture, we need to delve deeper into the fabric of the universe itself. We need to explore the very nature of space and time, and how they interact to create the phenomena we observe. Only then can we begin to understand the true nature of gravity, not as a force, but as a manifestation of the curvature of space-time. Isaac Newton, the brilliant 17th century physicist, gave us the first comprehensive model of gravity. His insights were revolutionary, changing the way we understand the forces that govern the universe. His law of universal gravitation stated that every object in the universe attracts every other object. This was a profound realization, suggesting that the same force causing an apple to fall from a tree also governs the motion of celestial bodies. This attraction, he proposed, is directly proportional to the object's masses and inversely proportional to the square of the distance between them. Newton's law was groundbreaking, providing a mathematical framework that could predict the behavior of objects both on Earth and in the heavens. It explained the falling apple, the moon's orbit, and the tides with remarkable accuracy. The simplicity and elegance of his equations allowed scientists to calculate the gravitational forces with unprecedented precision. His work laid the foundation for our understanding of the cosmos for centuries to come. Newton's theories were instrumental in the development of classical mechanics, influencing countless scientific advancements and technological innovations. However, even Newton recognized that his theory had limitations. He was aware that his equations, while powerful, were not the final word on gravity. It couldn't explain certain subtle but crucial phenomena. These anomalies, though minor, suggested that there were aspects of gravity that Newton's laws couldn't fully capture. For example, it failed to account for the slight wobble in Mercury's orbit around the Sun. This precession of Mercury's perihelion was a small but persistent deviation that Newtonian mechanics couldn't explain. This discrepancy, though small, hinted at a deeper truth about gravity, a truth that lay beyond Newton's grasp. It wasn't until the early 20th century that Albert Einstein's theory of general relativity provided a more complete understanding of gravitational forces. Einstein's theory introduced the concept of space-time curvature, explaining that massive objects cause a distortion in the fabric of space and time, which we perceive as gravity. This new perspective resolved the anomalies that Newton's theory couldn't. Today, our understanding of gravity continues to evolve. Scientists are exploring the mysteries of gravitational waves and the potential existence of dark matter and dark energy, pushing the boundaries of what we know about the universe. As we venture further into space and uncover more about the cosmos, the legacy of Newton's work remains a cornerstone of scientific inquiry. His contributions laid the groundwork for future discoveries, reminding us that the quest for knowledge is an ever-evolving journey. Enter Albert Einstein, a revolutionary thinker who dared to challenge the very foundations of physics. In the early 20th century, he proposed his groundbreaking theory of general relativity. This theory, far from discarding Newton's work, offered a more complete and nuanced understanding of gravity. Einstein's genius lay in realizing that gravity was not a force at all, but rather a manifestation of the curvature of space and time. Imagine space and time as a fabric. Massive objects like stars and planets warp this fabric, creating indentations. These indentations, in turn, dictate how other objects move within this warped space-time. Section 4. The Cosmic Trampoline. Visualizing Space-Time Curvature. Visualizing space-time curvature can be challenging. One helpful analogy is to imagine a trampoline. If you place a bowling ball in the center of the trampoline, it creates a dip. Now, if you roll a marble across the trampoline, it won't travel in a straight line. Instead, it will curve around the bowling ball, following the contours of the dip. In this analogy, the trampoline represents space-time, the bowling ball represents a massive object like the sun, and the marble represents a planet like Earth. The marble's curved path is not due to some mysterious force pulling it towards the bowling ball. Instead, it's simply following the curvature of the trampoline created by the bowling ball's weight. Section 5. Falling Freely. Experiencing Gravity's Illusion. Einstein's theory reframes our understanding of gravity. What we perceive as a force pulling us down is actually the curvature of space-time caused by the Earth's mass. We are not being pulled towards the Earth, we are simply following the natural curves in the fabric of space-time. Think about astronauts orbiting Earth. They appear to be weightless, floating freely inside their spacecraft. Are they free from Earth's gravity? Not at all. They are still very much under the influence of Earth's space-time warp. They are simply in a constant state of freefall, following a curved path around our planet. Section 6. Gravity in Action. From earthly orbits to cosmic lenses. The effects of space-time curvature extend far beyond our planet. It explains the orbits of planets around stars, the formation of galaxies, and even the bending of light around massive objects, a phenomenon known as gravitational lensing. Gravitational lensing is like a cosmic magnifying glass. When light from a distant galaxy passes by a massive object, like a cluster of galaxies, its path gets bent by the warped space-time. This bending can create multiple images of the distant galaxy, making it appear brighter and larger than it would otherwise. Section 7. The Universe's Grand Dance. Unraveling Gravity's Mysteries. Gravity, the invisible force that binds the cosmos together, is one of the most profound and enigmatic phenomena in the universe. It orchestrates the celestial ballet of stars, planets, and galaxies, shaping the very fabric of space and time. Einstein's theory of general relativity has revolutionized our understanding of gravity. This groundbreaking theory, proposed in 1915, describes gravity not as a force, but as a curvature of space-time caused by mass and energy. It has provided us with a framework to understand the universe in ways that Newton could only have imagined. Newton's laws of motion and universal gravitation laid the foundation for classical mechanics, explaining the motion of objects on Earth and in the heavens. However, Einstein's relativity expanded this understanding, revealing that massive objects like stars and planets warp the space-time around them, creating what we perceive as gravity. But the story of gravity doesn't end there. The universe is constantly expanding, and gravity plays a crucial role in this cosmic evolution. It influences the formation of galaxies, stars, and planetary systems, and governs the dynamics of cosmic structures on the largest scales. We are still grappling with many questions about gravity. Despite our advances, there are mysteries that remain unsolved. For instance, the nature of dark matter and dark energy, which together make up about 95% of the universe's mass energy content, is still unknown. How do these elusive components interact with gravity? What is the relationship between gravity and the other fundamental forces of nature? The quest for a unified theory that seamlessly integrates gravity with electromagnetism, the strong nuclear force, and the weak nuclear force is one of the greatest challenges in modern physics. What role does gravity play in the evolution of the universe? From the Big Bang to the present day, gravity has been a key player in the cosmic drama, influencing the formation and evolution of structures at every stage. What happens at the center of a black hole, where gravity is so strong that not even light can escape? These enigmatic objects challenge our understanding of physics, as the laws of general relativity break down in their extreme environments, leading to singularities where densities become infinite. These questions continue to inspire physicists and astronomers to push the boundaries of our knowledge. Through observations, experiments, and theoretical work, they strive to uncover the secrets of gravity and its role in the cosmos. The universe is a vast and mysterious place, and gravity, the architect of its grand design, holds the key to unlocking its deepest secrets. As we continue to explore and understand this fundamental force, we move closer to unraveling the mysteries of the cosmos and our place within it.